In this video 7, I will finally explain the language NSO, which is a Nullary second order logic. It is not really Nullary second order logic, so Nullary second order logic would be quantification over Nullary relations, but syntactically it is similar to it, and that's why we called it so. But now comes the second apology, that it used to be the first days of this language, which was maybe 3 years ago, more similar to Nullary second order logic, but maybe now it's less similar and we will need to maybe change the name. And the point is as follows. The main point is to have a language that can speak of its own sentences. Now, in the last video, I explained, I gave examples of countable atomless Boolean algebras, but there is another example, which is maybe the most important in logic. So let me say it here. Just before, I would just say here, the Cantor set concept is not a Boolean algebra, so we say Kloppen sets in the Cantor set. They make a Boolean algebra. Okay. A very important class of atomless Boolean algebras are Lindenbaum-Tarski algebras of logics with infinite signature. So if you have some logic that is closed under conjunction, disjunction, and negation, then its sentences make a Boolean algebra. This is called the Lindenbaum-Tarski algebra, the LTA, but in LTA, we treat logically equivalent sentences as the same sentence, as the same Boolean algebra element. So if you say X and Y, we treat it exactly the same as Y and X. Now, if you have infinite signature, it doesn't matter if the signature is infinite with constant symbols or function symbols or relation symbols. It doesn't matter. Why does it make an atomless Boolean algebra? Remember that in atomless Boolean algebra, you always have an element which is non-zero, but strictly less than a given element. Yeah, so let's write it this way. For all x exists y, such that if x is non-zero, then I can write the exists y here, but it's the same, such that y is strictly between 0 and x. If you have infinite signature, then you can always speak of another element from the signature that your x, this x didn't speak about, because each sentence is a finite string. You can speak only about finitely many symbols in the signature. So you can always have a y that speaks about something further, and by that get strictly smaller elements. By the way, so I didn't say anything about countable. I did say about atomless, but of course, all logics of interest are countable. Yeah? There are only countably many strings, where each string is finite and each character is from a finite alphabet. So we can see that the countable atomless Boolean algebra naturally appears in virtually all logics of interest. And again, they are all isomorphic. Whatever you say on one countable atomless Boolean algebra is true in the other, even if it's not countable, because the elementary equivalent we spoke about. So fix a logic L that makes a countable atomless Lindenbaum-Tarski algebra. NSO over L will be the language that we are about to show, but it will be decidable if and only if L is decidable. But for simplicity, let's think of L as just a first order logic, which of course will not be decidable. And now NSOL is going to be, well, what else? Of course, it's going to be the theory of Boolean algebra, interpreted in the Boolean algebra of itself. Now, to see it interpreted in the Lindenbaum-Tarski algebra of L, that's a bit easier. But my main point here in number 3 is a small point. What I want to say is as we said in previous videos, when we said the theory interpreted in some fixed Boolean algebra, we also assume that there is a constant interpreted to each element. In NSO, each constant is in curly brackets. We will see in a moment why it's important. So we can jump right away to an example, which should make it all clear to you. Just a random example. It's not that I prepared an example, but any example should make it clear to you. Let's say for all x is going to be a sentence in NSO, in NSOL. Now let's have x disjuncted with something. Okay, let's see what something we are going to put here. Is going to equal, let's say one of the Boolean algebra. So here let's put some constant. We said that constant is a curly bracket, and we said that a constant can be a sentence in NSO, right? Let's put another sentence in NSO. Exists x. Now this x is not the same x, right? It cannot be the same x such that, let's go for simplicity, for a simple statement, x equals x prime, which is of course false. Now, I could have also nested curly brackets and it would work exactly the same. Now let's see how it works. Let's do the standard quantifier elimination procedure that we studied before. So if we go by the algorithm we showed before, then we only saw how to eliminate existential. So we have to write not exist not. So here we are going to have not equal. And now we know that we need to have here equal 0. So we have to move the 1 here. And here write equals 0. And we saw that I just follow completely algorithmically. We saw that a function has a non-zero if and only if the union over, here I put, over its values in 0 and 1 are non-zero. So here I put 0, here I put 1. Now let's see what we are going to get. Here 1 union something, whatever it is. Oh, sorry. Okay, I made a mistake because this plus 1 should be on the outside. So I need to do this whole thing again. Now let's take the union over substituting 0 and substituting 1. So here x is going to be 1. Here x is going to be 0. Now one union anything is just 1. So I can simply write here just 1. 1 plus 1 is 0. So this whole thing is 0. 0 union something is just the thing. We got this. We can move the 1 right back here. And this quantifier is eliminated. Remove this negation by putting the equality here. And now we got another NSO problem, which is inside the curly brackets. And we can evaluate it. So exist x such that x equals x prime. That's of course false. So this becomes 0. So we conclude that this whole formula is false. And if we had nested curly brackets, we could run the quantifier elimination procedure and go to the next level. So in this way, you can see that if you have nested curly brackets of depth n, you can always proceed by induction and perform the quantifier elimination procedure, simplify the formula, and obtain a formula with quantifier depth n-1, and then you move on to n-2, until what happens at the bottom of the recursion. At the bottom of the recursion, there is no curly brackets, but we said that all constants are in curly brackets, well, except 2. So the only constants appearing in this bottom level are 0 and 1. And 0 and 1, if you have a formula in the language of Atomless Boolean Algebra where all constants are simply 0 or 1, then either it's true in all Atomless Boolean Algebras or it's false in all Atomless Boolean Algebras, and that's where the recursion ends. So we showed how we can make sense of a language that can speak of its own sentences, not only its own sentences, but also sentences of L. Yes, you could have here a constant from L, and then you wouldn't have nested curly brackets, but you could definitely have the product algebra, or in other words, the many sorted theory of Boolean algebra. So NSO can speak about many languages at once. So it can be L1, L2, and so on, including itself. There is only one thing I didn't mention. In this language that I showed, this NSOL, it doesn't make an atomless Boolean algebra. In fact, its Lindenbaum-Tarski algebra is just the two-element Boolean algebra, because all atomless Boolean algebras are elementarily equivalent. To make it a countable atomless Boolean algebra, all you have to do is to make its signature infinite. And for this, you simply add to it infinitely many uninterpreted constants, which, of course, you are very welcome to use. You can have a constant called, I don't know, good, and then you said this formula is good, this formula is not good. You can have a more expressive power, but most importantly, you made your LTA of NSO an atomless Boolean algebra. Let's write it. Add infinitely many symbols to the signature to make the LTA of NSO atomless. And that's the trick. That's how you can make a language that speaks about its own sentences.